Welcome everyone for the beginning of the academic year. It looks like the weather is beautiful and we hope for a very successful year. By the way, these are the best seats. I don't understand why people don't take them. Don't be afraid to be at the best seats. I mean, usually in other places people prefer the best seats. It seems like here people are shy. We are getting a bunch of new postdocs this year, and I sent an email about it. You can see their names of the order of 7. We also have the ITC Colloquium every Thursday, as everyone knows, here at 11 a.m., and so you're all welcome. Oh, great. And we just heard Javier Vian, right? I said it right.
You said it perfect.
Okay. From MIT, and told us about the fact that in the near future there might be opportunities to train AI systems better than students. That's what we are still waiting to see if AI will outperform many of us, but the day is not here yet. No. There is still need for humans, right, in science. Yeah. We have a number of talks today. So first, Javier will tell us, will speak. I don't have his...
I'm going to be talking about explainable AI technology that I developed some years ago.
Okay, so you will talk mostly about artificial intelligence, not natural intelligence.
Nothing about astronomy. That was the idea.
At some point, once AI becomes as capable as the human brain, then we might need to give it the same kind of privileges in academia, right? Then the question is, what do we do about tenure? What do we do about Nobel Prizes? Do we award AI systems if they make a discovery? These would be very difficult questions. Then we'll hear from Alon Gurman. He's visiting from Tel Aviv University. Where is Alon? Over there. Alon. And he will tell us about modeling the self-regulated cold interstellar medium in high-resolution hydrodynamical simulations. And after that, we'll hear about, from Zeyuan Xuan, who is visiting us from UCLA, talking about from gravitational-wave bursts to binary dynamics, unlocking the astrophysics of eccentric sources. Finally, we'll hear from our own Xingang Chen, where is he? Over there. And he will talk about exotic dark matter and the DESI anomalies. So we still don't know what most of the matter in the universe is, and it could be exotic. It probably is exotic no matter what, but actually Xingang will talk about things that were not thought about before. So I just wanted to mention also that Zeyuan Xuan from UCLA is visiting the ITC today and tomorrow. If you wish to meet with him, feel free to coordinate that. So we'll start, and finally there will be an ITC group photo on the 25th of September. That's a few weeks from now. So just be ready for that. And next week there is a conference here. They're holding it in this room, so we will meet in Pratt for the ITC lunch and also for the colloquium. So Javier, take it away.
Thank you so much. Let me connect the cable. There we go. Okay. So I'll be talking about this algorithm that my team and I developed some years ago, actually. But now that it's picking up sort of the lack of explainability problem in the AI world, I thought it was a good idea to give you a little bit of, an overview of some other tools that are not necessarily neural networks as we know them, but a different way of making predictions, right? That are also explainable. This is very much related with the previous talk that I was giving about, astronomy-related matters. But this one is only going to be talking about the algorithm itself, and it's a bottom-up architecture as opposed to a top-down approach where you have a neural network that is complex and you are trying to explain later on. So this idea of explainable AI is basically not just searching for the output as usual, but also looking for an explanation for every prediction that we're making. And that's the bottom line of this pipeline, right? We want to get outputs, but also explanations of the decisions. Right? What is explainable AI? Basically that, right? Something that can explain the rationale to the human. It's really important in many different areas, especially for validation, supervision, trustworthiness, and so on, certification. In astronomy, the two main concepts that we were talking about in the colloquium were the first, validation of predictions from an AI automated pipeline, and the second one, extracting knowledge or even doing science with it, as we saw in some particular case for star clusters. So this particular algorithm, it's using concepts of fuzzy logic that was introduced by Lofty-Zadeh many years ago, and 60 years ago or so, and concepts of deep learning as well. It's a deep learning fuzzy system that is combining concepts of clustering and the Takagi-Sugeno approach that I'll tell you later about. It's a very math talk, so please bear with me. But we'll start scaling. We'll go from the very bottom idea, and then we'll go all the way up to the very complex neural network that is not as the ones that we know of, that it's also giving you the explanations as it's doing. But the basic goal is to replace, for those of you that work with neural networks, is replacing the unit of a neuron, the neuron unit, and replacing it by something that can also give you an explanation as it's making the inference as you're progressing through the network. So yeah, the whole point of this is to cluster first, then train, and then predict and merge, right? So we cluster the input space. Let's say we have a very simple input, the horizontal axis, the x, and the independent variable, the y, right? You could do a clustering of the zones. Then you can train some sort of fitting a very simple line, and then having membership functions, the ones that we have on the bottom. And with those membership functions for each of those sets, they are fuzzy membership functions because they are not crisp. They are not either 0 or 1. There's a membership, a value all the way in between. With all those, you can then merge the values. So you obtain some sort of a smooth function from that clustering that you've done. And that's the basic concept, right? Then the parameter learning happens, and you're optimizing those lines over time. Each of those they have independent parameters that you could optimize for, and then you have the membership functions that you could optimize for as well. So you're learning. We use Cauchy membership functions that demonstrated. We have a couple papers about that, of why they are the most resilient and the most robust for this, to noise and different other things. And then we use this concept of Takagi-Sugeno, which is basically merging. It's just taking the weighted mean using the membership functions, but there's a couple other rules about that. And then we use the gradient-based optimization. Every neural network, most of the neural networks, unless there's a cost function that, some reward function or something, is always resorting to this concept of the gradient, right? What is the gradient? The derivative of the output with respect to the parameters that we have in the model, which could be the weights, the biases, and so on. So when you are taking that derivative, you actually look at the loss function. You can then look at the opposite direction of the gradient and move in that direction, so you converge into a minimum error situation. And that's the learning that happens behind every neural network. That's a compact formulation of this particular model and this particular algorithm. But it presents many interesting remarks and many interesting things that we can apply, right? So for example, for medical applications, we worked on one particularly where the doctor had this preconceived knowledge of how the oxygen flow affects the heart rate and the pressure, the arterial pressure, was affecting the oxygen saturation of the patient and so on, and we integrated that knowledge in the system. So what I'm trying to say is that this idea of having simple independent linear functions at a very unit level allows you to merge knowledge, expert knowledge in some cases. And you could put that, and then you have different membership functions, and then you can aggregate that. That's actually the case on the very bottom that I was telling you. So for example, there's one particular module of a fitted line and a Cauchy membership function that together they are maybe ground truth, or maybe even a theoretical formula and so on. Physics-informed models, they are somewhat resorting to these ideas as well in AI. But yeah, the concept is each of these modules are representing a group of line and a Gaussian or Cauchy, sort of that pair. And when we aggregate them, we obtain a very smooth and it's a universal approximator. You could put as many as you want and converge it to a certain an infinite degree of accuracy if you wanted in the training data, of course. Anyway, and we've also proved that it was more noise resilient than the current neural networks as they are now. But the basic idea is this one, that we can extract the linear function that is dominating the prediction, right? So imagine you have a certain instance, xi, you get the membership of that for each of those sets. The one that is contributing the most is the secondary set. We get that membership function. You obtain the prediction with that one. Of course, you have that complex, nonlinear mapping, which in the hyperspace is, a complex nonlinear mapping. But you can always get the hyperplane that is triggering that solution. And that is ultimately an approximation of the complex neural network. And that line basically is the explanation of the model. So you get the prediction, you also get the line, and this way you can understand what is the reasoning. How do we generalize this to n dimensions? Well, I can go through a little bit of the highlights here, but the basic idea is, well, the clustering is still happening. Instead of one continuous input feature, you have n input features. So you just parameterize everything in matricial shapes and so on, and matricial variables, and you end up having a very similar algorithm in the end. Every module is representing a Cauchy membership function that now has, this is the Cauchy membership function in the n-dimensional space, and then you also have a hyperplane like this one. And together they form a module, and they all aggregate, and this is the application of Takagi-Sugeno that I was telling you about before, which is just smoothing. It's a fancy way of saying to take the weighted average, and then you end up having these learning formulas that use this gradient descent approximation. But now, you could do synchronous or asynchronous learning. This is an example of how it works. So let's say input X, input Y, and then the prediction Z is what you're learning for. I didn't put them here, but there's a lot of noisy points that we try to train on. This is one case, this is another case, and this is another one. And what I was trying to show you is that it's very smooth, it's very nice. Usually neural networks, they are not this nice. Of course, if you train all the way down, yes, but the smoothness is very important, because what we are seeing these days of hallucinations in LLMs, when we work with ChatGPT, those sort of things, they come because of spikes, sudden spikes in these hyperspaces, because are very random instabilities that they develop those weird scenarios. But if you have a smooth hyperspace, everything is much easier, because you can sort of like control it better, right? Anyway. And I was showing the prediction against the truth, by the way. It's a little weird, the plot, because the colors are somewhat similar, but anyway. And you can, of course, extract the explanation. So you have the prediction flow, which is the nonlinear prediction, just a value. So you have an input X and an input Y. You go in here in this space, and you go all the way here, and that's the output. That's your prediction. But now you can retrieve the explanation, which in this case is it's a plane, because it's just 2 dimensions. It's a very simple problem, but you can extract from there this linear explanation of what's happening, of actual ground truth based on the dominant function. And last part, and I just have 1 more minute, I'll tell you a little bit about how do we generalize this, because that's okay. That's just n inputs, 1 output, just one particular neuron. But how do we generalize this so that every neuron in our neural network is exactly this concept, this algorithm? And we can do that by every single circle in whatever network we have, n inputs, L outputs, any of these points or circles, they are the exact same algorithm that I told you about. A little different. Instead, for the hidden layers, we have to apply logistic functions instead of linears. We can always trigger that linear approximation from that logistic function. But yeah, I'm going to skip a little bit through these, but the basic idea is to formalize it. And maybe I can jump to, there's a lot of formulas here, but some of the complex mappings that happen under the scenes of these pipelines are, we no longer have like an aggregation of n weights and then an activation functions. That's very simple. Actually, it's not really how the neurons work in our brain. There's many more things to that. The synapses, the liquid neural networks are picking up a lot these days because of the fluidity that they have and so on. Complexity at the unit level, I think it's critical, and the smoothness as well. And this pipeline allows you to do that. So anyway, and then there's different ways in which you can like update the different parameters and so on. You can configure the common architectures that we work on for the different pipelines, autoencoders, which I'm sure that you've heard of a lot of times when you process a spectra, for example, or images, to encode it into latent spaces. You can have an autoencoder like this that also gives you an explanation and perhaps understand much better what's happening in the latent space. And then also recurrent layers and everything. So it's the same idea, it's just that you replace the unit with another more explainable architecture. And well, the papers and so on, yeah. If you have any questions, happy to take them.
Javier, the challenge in the context of AI is that it's an exponentially evolving frontier with $1 trillion investment in the coming year, and that means it evolves in a timescale faster than the refereeing process in science. So by the time you write a paper and you say, oh, here is something we can use in science, there is something much better.
Yes, 100%.
And that is definitely every few months you see that. So how do you deal with that as a scientist?
I mean, if you're in explainable AI, you're in the wrong field because nobody cares about it. So it's unfortunate, but it's the truth. I mean, the industry is sort of driven by performance, and the explainability part. It's tricky, also very complex, because understanding what's happening from the network, you could either do it a bottom-up approach, like the one I just showed you, that is changing the entire architecture. I had to change like the formulation, the learning pipelines. I didn't show you the equations, but that was the most complex part of how to provide you the learning formulas for all the parameters of this pipeline. And that theory has to be developed for transformers, for many other things. But the other easiest approach is, well, let's work with a black box approach. We don't know what's happening. And now let's shake the box and see what's happening inside and try to figure it out, the reverse idea, right? The top-down approach. I don't know. I mean, there's different ways of approaching it, but I think people should, well, the industry should focus more on this. The academia has benefits, right? In the ITC Colloquium, I showed you 2 very useful cases, validating microlancing predictions and doing science with the star clusters. Both of them really valid. You could do theories, the Gaussian.
We can ask Ramesh if he's convinced that artificial is better than natural. Because he was not sure.
No, the world is changing, Aviv.
Okay.
So, yeah, I have no firm conviction.
You recognize your limitations.
I recognize my limitations, yes. But I have a question, though.
Go for it.
Go ahead.
So, the sensitivity analysis is really nice, explainability. But as I understand it, it says for a given conclusion that your black box reached, which of the various inputs contributed most and in which direction, right? The local.
That's more about the previous talk, though. But yes, you're going in the right direction.
Okay.
It's how much of the inputs are contributing to the output. Yes.
Right. I guess I'm still thinking.
No, but it's a very valid explanation.
Right. But my question is, the model was trained with some huge training data.
Yeah.
Is there a way of telling which subset of the training data contributed most to this final conclusion of?
You can run the same experiment on the training data itself. If you make inference of all the training set and then you aggregate the input contributions of every set, you can then quantify how much is contributing.
But has anybody done that? And
I do it in my day-to-day basis, but nobody can. No, I'm joking. But it's a very saliency maps, input feature contribution maps. There's some work on this. I feel like it should be more embraced in the astro community. Why not? I mean, it could be a good idea.
Okay, any other questions? Comments? Well, sounds like you're preaching to the choir because nobody has questions. Thank you so much, Javier.
Of course. It's already on. It's already on. What? Oh.
Okay, this on, great. Okay, hi everyone. My name is Alon Gurman. I'm a PhD student at Tel Aviv University working with Amiel Sternberg, who got his undergrad at Harvard College in 1980. And today I want to talk to you about metallicity dependence of C2 emission in a self-regulated ISM simulation. Before I start, I just want to plug this work is part of a bigger project we're calling the GHOST simulations. They're a set of high-resolution hydrodynamical ISM simulations. And we already have some interesting results. We have metallicity dependence of the H1 to H2 transition, C2 emission, CO to H2 conversion factor. We have high redshift or gas-rich suite, which we're working on. We've shown the importance of magnetic fields in those and working on C2 and CO emission there as well. So to start, to motivate this work, we're looking at the interplay between gas and stars. So we know in one direction, fairly trivial, we know gas cools and gravitationally collapses to form stars. And the other direction, we know we have stellar feedback, energy injection from stars into gas. So we know that we have radiation, photoionization, photodissociation, photoelectric heating, and so on and so forth. We have supernova shock heating and dispersal of birth clouds of massive stars, and additional feedback channels, which I won't discuss today, such as cosmic rays, stellar winds, radiation pressure. We know that star formation is inefficient from observations. Here we have an extensive sample from the FANGS collaboration where we see correlation between star formation rate surface density and gas surface density, but the timescales for gas depletion we infer from these observations are very, very long compared to cooling or free fall timescales of the dense gas, meaning that there's something that's making star formation inefficient, and that thing is stellar feedback. So this is what we call star formation self-regulation. So to model a self-regulated ISM, we take this approach where we try and model a neighborhood in a galaxy. So it's a box 1 kpc on the side, sort of a patch of a galaxy, and because this volume is relatively small, it allows us to work at relatively high resolution. So 1 solar mass resolution, it means we resolve the genes scale down to 0.2 parsecs, and we can run these for hundreds of mega years, and importantly for this work, at 4 different constant metallicities going from 0.1 all the way up to 3 times solar. Because the resolution is high, we can form and track the feedback from single stars. We do the hydrogen chemistry on the fly and carbon-oxygen chemistry in post-processing. And importantly for this work and for all of our other work, we post-process these simulations with radiative transfer codes to get synthetic observations of line emission in order to directly compare with observations. So let's just see what it looks like. So here we have the initial conditions. So this is edge-on, this is face-on projections of gas surface density. And once we let the simulation start, we have this burst of star formation, a lot of supernova feedback, and then we enter this breathing mode where we sort of form gas clouds, then they get disrupted by supernovae, and this cycle repeats. And if we look at the top right, we have the phase structure of the ISM. We have the shock-heated, hot ionized gas up top left. Here we have the warm neutral medium, cold neutral medium, and H2 regions. So the questions I'm going to be interested in for the sake of this project are related to metallicity dependence. So I'm interested in metallicity dependence of the C2 line intensity, the C2 star formation rate relationship, and its dependence on metallicity. Same question for whether or not C2 and H2 column density are correlated. And another question we answer is the origin. So which phase of the ISM does the C2 emission originate from? So start with an overview of the chemical structure we get from our simulations. So most of the mass is in H1 or C+, so that's a distribution of the general mass of the gas. And then when we go to denser environments, more shielded environments, we get H2 and C1. And at the very densest regions, we also have a core of CO. And the H+ traces the photoionized regions. Now we want to add the synthetic observations on top of that. So we post-process the simulation with a radiative transfer code called RADMC. And now we have these images where we are now looking at intensity maps rather than column densities. So an immediate interesting result here is that the C2 emission map resembles the map of H2 column density more than it does the C plus column density map. And that can be simply explained by the fact that H2 requires high density, highly shielded gas to form. And C2 emission, being a collisionally excited line with a high critical density, means that the denser gas is brighter per unit mass, which is why the emission is skewed towards the dense gas and looks like maybe an H2 column density map. Looking at it in a time-resolved manner, we can see here in black the star formation rate as a function of time and the H2 column density in red. And we see that both are fairly well correlated. This is, again, because both require high-density gas for star formation and high-density and shielded gas for H2 formation. At the same time, C2 emission is also correlated with star formation rate. And here it's because as star formation rate fluctuates, so does the far UV photoelectric heating rate. And that is, in the neutral gas, balanced out by C2 cooling, which is why we see the strong correlation between star formation rate and C2 emission. Now, what we can look at now is the way observers look at it, is plot the C2 luminosity, total C2 luminosity for each snapshot against the star formation rate. And each point here is a snapshot of our simulation. And the dashed lines are simple fits, linear fits, with respect to the star formation rate. And each color is a different metallicity run. So already what we see here is that it's approximately a linear relationship between the C2 emission and the star formation rate. And we see that the normalization of this relationship scales linearly with metallicity. Okay? And we can test that against observations. So we're going to look at the same figure, but now I'm removing the points from the simulation and adding in real observations from the dwarf galaxy survey, which took place with the Herschel Observatory in the early 2010s. And the points are now colored by metallicity. So the first thing we see is that there seems to be this positive correlation, but there's quite a significant scatter of order 1 to 1.5 orders of magnitude. And what we can do here to test the fit to our simulations is divide out the metallicity and see if the points all fall in a single relation. So now we have the same figure where the y-axis is now normalized by metallicity. And we see that immediately the scatter is reduced from maybe 1 or 1.5 orders of magnitude to something closer to a factor of 2. We see that the median line for the observations shown in red falls pretty close to our prediction for solar metallicity. So that this means we're predicting the actual luminosity correctly. From this, we take away that we reproduce the luminosity at a given star formation rate and metallicity, and that we explain away the scatter in the observations by simple variations in metallicity. So I'll summarize my main results. So first of all, we find an approximately bilinear relationship between C2 emission, star formation rate, and metallicity. We find the relationship between C2 emission and star formation rate due to just a thermal balance argument, where star formation rate determines the far UV photoelectric dust heating, and C2 emission has to balance that out. I haven't gone into details of that, but in our paper, we show that C2 is actually a good tracer for H2, even at low metallicity when CO becomes faint and undetectable. And very importantly, we reproduce the observed data from the dwarf galaxy survey and show that the scatter is driven mainly by metallicity. So just to say a few words on where we want to take this work. So as I said, we have this high redshift suite that I've published earlier this year. So I want to do similar work for CO and C2 for that suite. And at the same time, a bigger and more ambitious project is to add on-the-fly ionizing radiative transfer and to collaborate with the developer of COLT, Aaron Smith, who was an ITC fellow quite recently, to then make predictions, resolved high-resolution predictions for ionized gas lines, O2, O3, N2, N3, and so on, both in the optical and far infrared, which would help explain hard-to-explain observations, be it redshift 14 ALMA detections or even redshift 1, 2 gas-rich galaxies. And finally, we also we have work that looks at the effect of subgrid turbulence and subgrid clumpiness and its effect on the H2 fraction and the CO mass and how that can resolve some tensions with observations. Yeah, so I'll finish here and take questions. Thank you very much.
Thank you, Alon. Of course, C plus can also result from a central AGN, right? Because it could illuminate the surfaces of regular clouds, even without the stars doing that.
Yes, to
Consider that external illumination by AGN, or that's not possible?
well, that's definitely a potential extension of this work. Because of the periodic box setup, it's more, I would say, more appropriate for normal star-forming galaxies. But it's definitely a direction you can think of taking it in. I think that would only be applicable once we have the full radiative transfer module implemented, because right now we don't have we can't do it approximately. It wouldn't be really useful. Yeah.
Questions? Vadim? Go ahead.
They're interesting. So I was wondering, the stuff from instruments are instantaneous or averaged over some time scale?
So it depends on what you're looking at. If for the far UV heating, I think it's 40 megayears. I think I was showing 40 megayears in the figure. Yeah.
Does it matter that the ISM is actually in steady state on this time scale, or if you have a starburst, will the correlation still be there, or what would you expect?
Well, that's an interesting thing to check, and I hope that the gas-rich boxes that I run can illuminate that. But this is a gas surface density of solar neighborhood, so it's not that bursty. It's quite bursty at 0.1 metallicity, and I can maybe show you the figure later. But when there's troughs in the star formation rate, the C2 emission is dominated by the warm neutral medium, at which point the relationship breaks, and there's sort of a floor value which you hit. But it'll be interesting to see what happens in starburst conditions, and I'm going to look into that.
I think this is a little bit related to what Vadim was just asking, but one thing I was struck by in seeing the whole calculation is it felt like a lot of the turnover was dominated by the size of the periodic box, and like that size scale was sort of imprinting that largest scale cyclic behavior.
You mean the time scale for?
Yeah.
Well,
so does that not then cascade down into all these relations, or why are they independent of that?
So I've tested this with like 3 times, like a volume 9 times as big as well, and the time scale seems to be pretty similar. It's determined by the cooling time of the hot gas, which is why in the low metallicity runs the time scale for these fluctuations is longer.
What is the sound crossing time across your box? Of sound waves?
For the warm gas?
Yeah.
I don't know if I have that off the top of my head.
Because that would address, I mean, if that time is very long, that would be fine. Then the box
But I don't think the warm gas crossing time is important, but rather the supernova bubble effect. Like, because that's a fast moving gas.
so
But that's something to look into. I haven't checked that. But I've just tested like very large boxes, which seem to have the exact same behavior.
Yeah, so I guess that's interesting.
Yeah.
Any other questions? Lisa, go
I'll
ahead.
just defend you and say that when you look at images, the sizes of the biggest bubbles are typically a little bit less than a kiloparsec. And so it's probably not a
Yeah. Okay. Yeah. Interesting.
I mean, the arms
Yeah.
But another way to address it is to have a bigger box, like go to a full galaxy simulation.
Well, he already
No,
did
no.
experiments with a bigger
Yeah.
box, and you get the same answers.
It may
Yeah.
actually be bigger.
Yeah, I'm sure it does.
Very nice
Okay.
work, Alon.
Thank you.
Hooked up. I just want to thank Eric Quito for making this happen. So, the ITC, Eric, because he's speaking with her next. Anyway, science is more.
All right. So hi, my name is Zeyuan Xuan. I'm a final year PhD student in UCLA working with Madanaus. So in today's talk, I'm going to focus on a population of gravitational wave source that is less commonly discussed before, which is highly eccentric compact object binaries. And I'm going to show you that these systems can actually have quite promising population, especially for the mid-Hertz gravitational wave observation. Okay, to start with, we know that since the first detection of gravitational wave by LIGO in 2015, there have been many proposed formation channels to explain the merger rate we measure nowadays. And among all of them, one of the major categories is so-called dynamical formation. For example, there can be gravitational wave capture and scattering in dense stellar clusters that bring two compact objects into close distance. There can be flyby perturbations that perturb the wide compact object binary in the galactic field and make them merge. Also, even in a most general configuration, if you have a stellar mass triple system, the distant tertiary companion can perturb the inner compact object binary through the cosine of oscillation so that the system can be excited to high eccentricity and merge via this channel. So as you may notice, actually in many of these dynamical formation channels, there's a common mechanism for which the universe makes two compact objects into close distance. In other words, the system is likely to start from a wide binary configuration, just because wide binaries are common. And through some perturbations, the eccentricity is excited. The pericentric distance is reduced so that the gravitational wave radiation power is enough to make the system merge within a Hubble time. Therefore, if dynamic formation turns out to be a significant contributor to the merger rate we measure nowadays, we should expect to see lots of eccentric systems as a natural consequence. So next, to demonstrate this, these systems' population and dynamical arrangements, I'm going to show you a few examples based on my previous studies. First, we know that in many galaxy centers, there's a supermassive black hole surrounded by a nuclear star cluster. And in the dense stellar environment of those nuclear star clusters, there can potentially host lots of compact objects, including compact object binaries. So for example, from our group's previous simulation, roughly 10% of all the stellar mass binary hole system in the galactic center will merge eventually because they are perturbed by the central supermassive black hole through the eccentric Gauss-Leidov mechanism. And here, what I'm going to show you is the typical parameter for their different evolution stages. So first, the binary is likely to start from a wide configuration, like with separation between 0.1 to 100 AU in the galactic center environment. And for those merger systems, the eccentricity is excited to extreme values, such as even 0.999. And at this stage, as you may imagine, the system effectively bursts energy once per orbit during the pericentric passage because the distance is short, while they will remain quiescent for all the rest of the orbit period. So they will gradually lose energy with a timescale of 1 million years. And next, the system will shrink and circularize under the effect of gravitational wave. For example, when it reaches 10 to the minus 3 AU, the eccentricity is also likely to drop to moderate value, such as 0.3, 0.5. So these systems are actually the quasi-circular in-spiral that we commonly discuss in nowadays mid-Hertz gravitational wave observation, which lasts for thousands of years for stellar mass case. And finally, the merger happens, which emit high-frequency gravitational wave signal that we observe nowadays using LIGO. So there are two main takeaways from this picture. The first is that, as you can find, even if the current observation hasn't found convincing evidence for the residual eccentricity of the merger system, in the future, with mid-Hertz observation, we will definitely look into their much earlier evolution stage, where the system will have moderate or even extreme eccentricities. Secondly, and most importantly for this talk, is I like to highlight the timescale here. So as you can see, the timescale, or basically the lifetime of highly eccentric progenitor system can actually be much longer than the circular in-spiral that we commonly discussed. If you think about it from a population viewpoint, the longer lifetime a stage lasts, the larger expected number they will have. Therefore, if we naively take a snapshot of the universe, let alone the detectability, in principle, this highly eccentric progenitor can be hundreds to thousands of times more than those circular in-spirals. But of course, you may ask me, why not include their detectabilities, right? So if you, as I explained before, these highly eccentric systems have a longer lifetime, basically because they only burst energy once per orbit. So the average power of emission is suppressed. This also means their detectable distance is limited because they have weaker signals. But as I'm going to show you next, even if you include back this detectability criteria, this highly eccentric system can still have promising or even dominant population in the local universes detection. Okay, so to demonstrate this point, we'd like to look into a bit more details about their waveform. So I'd just like to highlight that the waveform from highly eccentric system, as you can see in blue on the top, is very different from the quasi-circular signal of gravitational wave. So basically, because of the high concentration of energy during the Paris-Sun passage, the waveform is basically a repeated burst that is separated by the orbit period. While the commonly discussed in-spiral is like a monochromatic sinusoidal wave, as you can see in red. And also, it means the frequency domain spectrum of the highly eccentric gravitational wave is very different. It's basically like this blue shaded region. It's made up of a clustering of millions of harmonics, which spreads the energy in a wide range of frequency. So this, of course, causes challenges to detect these systems. But as a basic estimation of detectability, we can sum over all these harmonics energy and estimate the signal-to-noise ratio, which can help us infer a maximum detectable distance for different orbital parameters of these systems. So in the right side, I'm going to show you the maximum detectable distance for a 10 plus 10 solar mass binary black hole. Basically, this parameter space is highly eccentric ones, while the top left is the commonly discussed millihertz in spiral. So as you can see from these labels on the dash contours, basically highly eccentric stellar mass gravitational wave source will be detected within a dozen kiloparsec distance, up to 1 megaparsec. So such a detectable range is, of course, much closer than the millihertz in spiral, which can be up to redshift 0.1. But it's still good enough for detecting those systems in the Milky Way and a few nearby galaxies. So motivated by this point, my previous research did the population synthesis of this binary population, from galactic field, galactic center, and global clusters of the Milky Way. And we find that even if you only include this highly eccentric binary black hole population, you will have a few dozen detectable systems, which contribute to thousands of births per year. And this result is also confirmed by Monte Carlo unbounded simulation. So this plot is taken from my recent work with Kyle Kramer and Spadanaus, for which we use the Monte Carlo unbounded simulation of global clusters and fit the simulation to the observed properties of Milky Way global clusters. So basically, we create a mock sample of binary population held within the Milky Way, which is shown here in each dot. Basically, the x is orbital frequency, the y is the gravitational wave frequency. And those dots with larger size on the top are the detectable system in millihertz. So our simulation finds that roughly 50% of the system will be detected with E greater than 0.9. This is purely from Monte Carlo unbounded simulation results. First, it's consistent with the point that I just made before. And secondly, I just like to highlight that the usage of this highly eccentric system is not only contributing to a population. So for example, to the right side, I'm showing you a picture of Omega Centauri, which is one of the Milky Way global cluster. And overplotted in this green dash contour is the Bayesian inferred sky localization error for a gravitational wave signal from a simulated binary system in this global cluster. So you can see by eye, just by eye, once detecting this system in the future, we can directly correlate their spatial location with the host environment in the Milky Way, and which serves as a strong probe of their formation channel and basically a strong constraint. And of course, the story of highly eccentric system is not limited to the two examples that I gave in this talk. For example, if we neglect them as what we are currently doing in the data analysis of millihertz, they can create a stochastic background that exceeds the instrumental noise, which is shown in my previous works. So they may interfere with the detection of other sources. But instead, if you look into their template and include them in the fitting, they may create some unique time frequency pattern in data analysis, which can help us disentangle the system. And also, eccentricity in gravitational wave in general enhance the parameter measurement accuracy because it breaks the degeneracy in the waveform analysis. So using the highly eccentric gravitational waveform, we can have 1 to 2 orders of magnitude more sensitivity to the environmental effects, such as if the system is surrounding a supermassive black hole, then the sensitivity to the peculiar acceleration induced by this third object will be enhanced. The sensitivity will be enhanced. And finally, some of these highly eccentric systems can have multi-messenger signatures. For example, in my most recent work, we show that some black hole white dwarf system can have highly eccentric gravitational-wave precursor before they become an ultra-compact binary system. So it's like a multi-message detection. Okay, so perfect timing. So I will leave this slides for summary and happy to take questions. Thanks.
So, Xuan, you started from binaries that have a separation between 0.1 to 100 AU, and my question has to do with tidal disruption by passing stars, because these are very dense environments in galactic nuclei that you get up to 10 to the 7, 10 to the 9 stars per cubic parsec.
Yeah, exactly.
Did you check whether such systems would survive?
Yes, it's a very good question. So basically, these so first for a question in galactic-centered environment, a separation of 100 AU is actually a bit dangerous, like the evaporation time scale and two-body relaxation basically can break the system. So in our simulation, we was so that we get 10% of the system merged. That number is from including this effect. So basically, some systems will not survive, so they're just erased out of the population. And actually, this question can be more severe for the wide galactic field merger, where you have like 10,000 AU separation and perturbed to like very extreme eccentricities. So that case will have even more concerning effect of flyby or evaporation, basically.
In our galaxy, the center that you can see with the LISA, say?
So roughly a few, from the galactic center. But if you sum over and equate together, should be a few to a few dozen.
So by the time you get your tenure, that should be observed.
Yeah. Hopefully.
Within a decade. Questions, comments? Okay, please.
Great talk. I was wondering if in your population synthesis analysis, is there output about binaries with a neutron star black hole binaries, where one of them is a radio pulsar, for example? How many of them could exist in our galactic center or in the Milky Way solar black clusters? Any numbers of those?
Yeah, it's a good question. So actually, in our simulation, like in my PhD research, I'm mostly focused on the binary population. But I know there are a few works that's recently discussing the binary, like a black hole neutron star merger from where the dynamical formations. There's a recent work by Jakob Stegman, about that, which can explain some eccentric gravitational-wave merger. So maybe we can talk about that later. Yeah.
Any other questions? Not, let's think. Run again.
All right. So this talk is based on work done recently in collaboration with Aviv and brilliant postdoc Mattia Braglia, who is now at the CERN. Now this work is motivated by the recent publication from DESI collaboration, especially data release 2. DESI is using BAO as standard rulers and supernova as standard candles to measure the expansion history of the universe, especially late time. So they have found something interesting. They have found some evidence which is not decisive yet, but large enough to be interesting, generate a lot of interest, that the late time expansion of the universe may appear differently from what the standard model predicts. So in standard model, the dark energy sector is equivalent to a cosmological constant. What DESI DR2 suggests is the dark energy density may be evolving. It not only evolves, but evolves in a very surprising way. The data analysis that leads to this conclusion has been discussed by many speakers last semester, by Daniel, Christine, visitors. So I'm going to skip that. But just to summarize it in a way that is relevant to the main point of this talk. So to show the evolution of the universe, I plot the Hubble parameter as a function of time. Time can be scale factor A or redshift Z. I subtract the Standard Model from the result. So that was delta means here. So that means the dashed line is the Standard Model prediction, 0. So to show you what the DESI result is, let me first give you some toy models of dark energy models. So I show some models which is not the Standard Model by changing the equation of state for dark energy. Equation of state is the pressure divided by density. So here, here is example, the orange line, example where W is a little bit larger than -1, so -0.9. So those models are, for example, they are so-called quintessence models in which W is always larger than -1, but it's not necessarily constant, but drawing a constant to give you a rough idea. So because W is no longer -1, so it decays instead of being a constant, so we need a little bit more dark energy in the past so to reproduce the number of Hubble parameters that we measure today. And of course, dark energy is not going to compete with dark matter and radiation in the past, so in the past, it's also not visible. So you see a bump in this evolution. And you can try a W which is less than -1, you'll see the opposite effect. What DESI found is you have an evolution of dark energy which start from W less than -1 and crossing to -1 and become larger than -1. I'll give a fancy name, phantom crossing. So that means at some point where it crosses the Standard Model value -1. Okay, so the evolving self is already surprising, but the main troubling feature of this claim is the part where W is less than -1. If you have a model, a sector which has W less than -1, it violates null energy conditions. The consequence is if you try to UV complete it and do some microscopic physical realizations, you often run into troubles. So if you're not familiar with the terminology null energy condition, we can look at a simple scalar field theory realization of dark energy, in which the kinetic K is the kinetic energy of the field theory, and the V is the potential energy of field theory. Well, if you have a constant, cosmological constant, K, kinetic energy is 0, so you have W equals -1, no problem. Kinetic energy usually is positive, always positive, so it's no problem, at least mathematically, to get W larger than -1. But if you want W less than -1, you need a negative kinetic energy. So you need to put a negative sign in front of a kinetic energy. So that means it's a runaway behavior, and there's no lowest energy state. So theoretically, it's a problem, although you can fit it just by parameterization. So the natural question is, do we have alternative explanations? Well, indeed, people try several things, has several proposals. And recently, we give a new proposal, which actually, in my opinion, is the simplest proposal. So we decide to keep the dark energy still a constant, good old constant, and we only change the properties in the dark matter sector. Now, in Standard Model, a dark matter sector is cold dark matter, with W equal to 0. And we propose to look at we introduce a small component of exotic type of dark matter. We call this exotic dark matter. The property definition of this is there's a species of dark matter whose equation of state deviates from 0 only at late time, but within -1, so it doesn't violate null energy condition. So let me give you a few examples what the exotic dark matter does for the Hubble parameter evolution. So here is a time evolution of a W, so it's 0 in the past, and then become negative. and this is the present. Okay, this is the present. Because the dark matter has a negative equation of state, so it decay a little bit slower, so you see this bump here. And also because the presence of this exotic dark matter decays slower, you have to change the energy budget of the dark energy, the constant, make it less. So in the future, in order to recover the present day Hubble parameters, this bump has to reduce. This rising behavior has to decay. So you see a bump behavior. It's interesting that if you compare the previous dark energy model, a deficit in the W for dark matter actually produces the similar effect for a surplus of W in a dark energy sector. It's kind of a little counterintuitive, but it's easy to see from Friedman equation and numerical examples. And you can do a opposite example, and you will see a dip. And also, because we changed the dark energy in the dark energy budget in the past, there's a little bit effect here, which you don't see very clearly because we have only take one special example, but I will give you some other examples. So you can, of course, to play around with the form of W evolution, make it oscillate, you can generate all kinds of evolution of Hubble parameters. So you can change the late-time universe very freely. So obviously, we would like to look at a specific simple example and try to fit data and explore all the parameter space. So here is a simple model that we tried, just one step. So you have a W value, transition at a particular A or redshift point. And we say the fraction of this exotic dark matter in total dark matter is labeled by F. So it's a 3-parameter model. So let me fix the 2 parameters and vary one of them just to show you the qualitative feature. So we explained that the negative W will give you a bump in the evolution. Also, I mentioned that because of the presence of this exotic dark matter, you have to adjust the energy budget for the cosmological constant, which has no effect in the past, but show up close to the late time. It's interesting that so this generates a shallow change. Here I also plot the best fit data from the dark energy model from DESI collaborations. As you can see, they also have a shallow change and a bump, as we showed previously with a phantom crossing. So it's interesting that just by introducing a simple step, you actually reproduces both features. So if you insist the dark matter is cold dark matter and try to fit this within dark energy model, you will have to interpret it with a phantom crossing the dark energy. And of course, you can vary some other parameters, and you can give some examples, but clearly you can see now why data analysis could work by varying different parameters, because they are going to reproduce the observations. Because the model has different parameters and different range, we decide to do model comparison in a Bayesian approach to taking into account, to penalize introducing extra parameters and to taking into account the look elsewhere effect by computing the Bayes factor. Here is how to interpret Bayes factor. So here is the result. So I'm showing the Bayes factor here. The negative means it supports beyond the standard model. So here is 2 beyond standard model. One is dark energy model, another exotic dark energy model. So if you use DESI DAO data plus CMB plus supernova data, DESY year 5 data, and you've actually found strong evidence favor for beyond standard model for both cases, and same for Union 3 supernova data. But if you use Pantheon supernova data, you find no evidence, even a little bit disfavored, same as if you don't use any supernova data. So the conclusion is the evidence for beyond standard model is not decisive. Evidence also depends on supernova data sets, which is the most puzzling aspects. And also, another conclusion is EDM performs similarly to dark energy models in terms of this DESI style data fitting, and is an alternative framework. So I'll go this very quickly. So a natural question is this easy to construct? Right? So yes, you can have a perfectly fine scalar field models with a normal kinetic energy, but just change the potentials. If the potential is a harmonic oscillator, you get W equals 0 because kinetic and the potential energy on average, they cancel. If V is constant, you have -1. Everything in between, you have some more arbitrary values. So here's an explicit example. And the density of dark matter is proportional to the amplitude. So if it's at large density past when a universe is small, you look at the potential from large scale, so it's almost harmonic, W equals 0. When you zoom in, redshift, oscillation, redshift, the amplitude drops, and you start to see some strange shapes. And eventually, you will see W equal to -12. And here's the existent proof this kind of potential exists. So this is a landscape. You zoom in, you see bizarre shape. And at the bottom, you see trees, rocks, and somebody's backpack.
That's point minus 0.5?
Probably. Or something else that you see in the future. Okay, so I only fit the background. There's a lot of things to do in the future to check structural growth, matter spectrum, CMB weak lensing, and full data comparison. Let me just end with a short comment. So DESI has built one of the most powerful telescopes and started taking interesting data. But even before they took any data, they decide this device is going to measure the property of dark energy. So that's what the name suggests, dark energy spectroscopic instrument. And this plays some role in terms of shaping the direction of the research and the common wisdom, because when an anomaly came up, most of the paper is devoted into investigating what's wrong with dark energy, or at least something related to dark energy. But maybe in the name, the collaboration just made a small typo. What DESI really meant to be is EDSI, Exotic Dark Matter Spectroscopic Instrument. Okay, thank you very much.
So what you're saying, Xingang, is often we find what we're looking for. Therefore, we should be careful because it may not be that.
Yeah.
Any comments, questions? If true, this would be really important.
Yeah, there's a lot of things to check as well. Yeah, just start.
And including perturbations and the growth of structure.
Exactly.
Model. So any young person in the audience interested in doing perturbation analysis, growth of structure in this model is most welcome to speak with Xingang.
Thank you for the advertisement.
Questions, comments?
When you do that round of tests, do you kind of expect there'll be some allowed range of models or allowed range of the value of W as a function of time? Like what is, will you kind of look for a constraint in that space, right? Between -1 and 1? Okay.
Yeah, so definitely it's model dependent because here we just try the simplest one, it works already. So that definitely, if you look at the posterior distributions, tells you what value of W it prefers. Yeah. But the point is, compared to the W from dark energy sector, it's completely different behavior. Yeah.
Of course, it would be interesting to see if there's any effect on galaxies, right?
Yeah, that's a very interesting effect too. This is a very interesting effect. So usually you study dark matter, you want to study a cluster in the galaxy where dark matter has high density. But here we are looking at the property of dark matter of average density in today's universe. It's very low. So the ideal place to study exotic dark matter in astrophysics is instead of looking at the void when the density is very low. That's the part relevant to cosmology or even future cosmology. Yeah. Because if you have high density, that means high amplitude, and you just see m squared, phi squared, harmonic potential. So it's also good because we get around a lot of astrophysics.
Two remaining questions. One and then.
What are you going to look for in the voids?
What I'm going to look for in the void?
What would be the effect in the void?
What tracers are you going
to look for? Yeah, that's a very good question. I just started to think about that. Maybe it would, I don't know, maybe morphology of the void, statistics of the void, etc. Yeah, very good question.
Galaxies that are in the void will behave differently than galaxies elsewhere.
Yeah, because
They are, yeah. Okay, last question.
If EDM is real, like what do you anticipate the imprint is to the lower redshift or even the local universe?
can you say it again? What's the imprint of
EDM on like the lower redshift in local universe?
on the local universe?
Other than the expansion of the universe,
Oh, yeah.
are there any other signatures?
Yeah.
Yeah.
So what I showed is only expansion. We plan to do perturbations. For example, it will impact growth, structural growth, although it mimics the background, which makes it a little bit safer because it completely mimics background of dark energy. But the perturbation of cold dark matter, because the budget changes, and we have to study the perturbations of exotic dark matter itself. So that will change the inhomogeneities, will change the lensings of CMBs, will change maybe redshift distortion of galaxies. So that will be local observational effects.
So basically, the dark matter is not cold when you consider low density regions, and that could have interesting effects.
It's not cold, yeah.
Wherever you have low density of dark matter, the dark matter will not behave like cold dark matter. Okay, it will have very high pressure.
Yeah, so this is also related to,
that can be looked for, in principle.
Yeah, so this is also related to the previous question. So if you work out the consequence, just try to compare with the standard model prediction. Everything different will be interesting. Yeah.
Okay, let's thank Xingang again.
Thank you.